Okay, first I want to go through this handout on it's Pascal's triangle and combinations. This is if you go back to the original Pascal's triangle. Remember, Pascal's triangle always starts out with a 1 and then 1, 1, and then you add ones down the diagonal, and then you add the two numbers above it to get 2. Add the two numbers above it to get 3, add the two numbers to get... So here's the Pascal's triangle, the 1, 1, and then the 1, 2, 1, 1, 3, 3, 1, okay? But you can use Pascal's triangle instead of, if you didn't have a calculator, okay, or to save time, you don't want to type it all in, okay, you can use this Pascal's triangle to do combinations. So if you look at the bottom down there, and this actually goes back to an older book that wrote it like this. Number of combinations of 8 elements taken 3 at a time. And they've numbered these rows. The first row is actually numbered row 0. Okay, and then the second row is actually first. So when you look at combinations of 8 elements taken 3 at a time, okay, you go down to row 8. Okay, go diagonal 3 and go across and read that answer. Okay, so you're going down and coming across here and read that answer. Okay? So within Pascal's triangle, you get all those combinations. Okay? Which is pretty slick. Okay? Okay. So if you did another one, say combinations of 6 elements, you know, and we wrote it like this, combinations of 8, 3, but some authors write it like this. This one would be combinations of 6 elements taken 5 at a time. So you'd go down to row 6, okay, and then you go diagonal 5, okay, and then you come across and find your answer. Okay. Okay. So that handout is basically just a reference sheet for you for and to know how many different things are in Pascal's triangle. You have to stop and appreciate what this man did as far as mathematics. Super amount of, okay. So keep that in your notebook, but if as you're working these problems today, I think this handout will save you some time, okay, if you just use that, okay. Okay, then I want to go through the notes on, this is actually on 13.6. And this ties in with what we did on the binomial theorem. And we're going to tie it into probability. Okay. And remember, on the binomial theorem is where we took a binomial to any positive power n. Remember, the first term was always the first term to the n power, the second term to the 0 power, plus, and then the coefficient in front of the second term was always this exponent over 1. And then it was a to the n minus 1 power, b to the first. We went descending in the a exponents and ascending in the b's. To get the coefficient of the next, you took this exponent times the number in front. So it was n times n minus 1. And we went over, put 1 times 2. We went up, multiplied by the next highest number. Then a to the n minus 2, b to the second, plus. Let's go one more. Take that exponent times the number in front. So it's n times n minus 1 times n minus 2. And it's all over 1 times 2 times 3. A to the n minus 3, b to the third, plus. Then dot, dot, dot to show we left out terms. And you go all the way down to a to the 0 and b to the n. That's where it stops. Now, you don't have to write that formula out, you just have to be able to use it. Okay? When we do the binomial theorem, this can be written another way. Okay? I showed you with Pascal's triangle, okay, but now I'm going to show you with the combinations. Okay? This coefficient in front of this, if there's nothing there, it's understood to be a 1. Okay, and that is actually the combinations of n elements taken 0 at a time. Okay, and it's a to the n power b to the 0 plus. So this is that combination. Okay, for this coefficient, that is the combinations of n elements taken 1 at a time. Okay, so that's that combination. And then a to the n minus 1, b to the first. This coefficient, combinations of n elements taken 2 at a time. And then a to the n minus 2, b to the second. This coefficient, you get the idea, combinations of n elements, and the n is your exponent on the outside. 3 at a time, a to the n minus 3, b to the third, plus dot dot dot, on down to the coefficient in front of here is understood to be a 1, and that's combinations of n elements taken n at a time, and it's a to the 0, b to the n. So all those coefficients are now going to be combinations, and you can use that handout, or you can use your calculator to do the coefficients in front. Okay, all of these problems are going to be what they call binomial experiments. Okay, and a binomial experiment, certain things have to be true for it to be a binomial experiment. First, if you're looking at binomial experiment exists. IFF, if and only if the following exist or are true. Okay, number 1, the experiment, and they call it an experiment. It can be just, an event. The experiment consists of n identical trials. That means, like, if I'm flipping a coin, okay, I'm flipping the same coin, just flipping the coin in identical times, okay? Each trial results in one of 2 outcomes. It has to be binomial experiment, so there are only 2 outcomes. Like if I was flipping a coin, the 2 outcomes are heads or tails. It's never going to land on an edge. Okay. The third thing, the trials are independent. All of these have to be true for it to be a binomial experiment. The trials are independent, so what I do on one toss has no effect on what I do on the other. The trials are independent of each other. Okay. And the probabilities, fourth step, the probabilities in each trial are the same. Like if I said, what's the probability of landing on a head? 1 out of 2. What's the probability of landing on a tail? 1 out of 2. Okay? Okay, now let's look at an example. Say 5 coins are tossed at the same time. Okay, so instead of taking 1 coin and tossing it 5 times, I'm taking 5 and tossing them all at the same time. What is the probability that exactly 2 coins will show heads? I want exactly 2 coins to show heads. What's the probability? Okay, now, when you set this up, it makes a difference in your binomial which one you put first as to, and I'll show you when you set that up. Like I'm going to figure probability of heads plus the probability of tails. Those are my two outcomes, heads or tails. How many coins am I tossing? 5. That's my exponent. Okay. Now, you need to look at this. Exactly 2 coins will show heads. When I start expanding this one, if I do combinations of 5 coins taken 0 at a time, probability of heads 5, probability of tails 0. Okay, then I do combinations of 5, 1, probability of heads 4, probability of tails 1. And I want to get exactly 2 heads. Right now I've done 5 heads, 4, so combinations 5, 2, probability of heads 3, probability of tails 2, plus combinations 5, 3, probability of heads 2, probability of tails 3. Now, which one? I want the probability of heads 2. Yep. So I want exactly. So I want this term. Okay, now look on your chart. What's combinations 5, 3? You either do it on your chart or you do it on the calculator. What'd you get? 10. So that's just this part is 10. Then you have to say, what's the probability of it landing on heads? 1/2, right? Okay, 1/2 to the second power. Probability of tails, 1/2 to the third power. Now, these two are the same. 1/2 is the base on both of them. So that's actually like 1/2 to the, when you multiply those, what do you do with the exponents? Add them, so that'd be like to the 5th. So this would be 10 times 1 to the 5th, and 2 to the 5th is 32. So 10 over 32, and reduce it to, 32. 10 over 32, and that'll reduce to 5 over 16, and they may go to decimals or percents, and that's actually about 0.31, or 31% of the time. That's the probability that exactly 2 will show heads. Now, I said it makes a difference how you put these in. If I had reversed these two, would I get to my answer sooner? Yeah, it would have been this term, wouldn't it? Yeah. So when you're thinking about these, and it makes a difference as this exponent gets larger. So if I had reversed this, if I had done this and turned those two around, I would get to my answer sooner. Okay? So think about how do you want to write those two probabilities. Okay? Okay, let me give you one more example. Oh, let's go back to this a minute. If I had changed that, and I don't have to write the whole thing out, but if I had changed the words in this problem, if I said, what's the probability, this one says the probability that exactly 2 coins will show heads. What if I said, what's the probability that at least 2 coins will show heads? At least 2 coins will show heads? Doesn't that mean 2, 3, 4, or 5 coins show heads? So then I would take and I would have to figure out each one of these and then add all 4 of them together. Okay, so key words in there, like at least, makes a difference. Okay? Okay, let's look at another example real quick. Okay, on this one, the probability, just abbreviate it, the probability that Phyllis will win whenever she plays bridge. Bridge is a card game. Is 1 out of 4. That's the probability she wins. What's the probability she loses then? 3 out of 4. It always adds up to 1. Okay? Suppose she plays 6 games. Find the probability that she will win four times and lose twice. Okay, so you're still going to set it up now. You got to decide which way you want to go. You want the probability she wins 4 times, lose twice. I'm going to do probability she wins plus the probability she loses. She's playing 6 games. Okay. So combinations 6, 0. Probability she wins 6. Probability she loses 0. Plus combinations 6, 1. Probability she wins 5. Probability she loses 1. Plus combinations 6, 2. Probability she wins 4. Probability she loses twice. And that's the only term that they're asking for. So now you look on your chart. Combination 6, 2. 15. Probability she wins. Phyllis is not a very good bridge player. 1 out of 4 to the 4th power. Probability she loses. 3 out of 4 to the 2nd power. Okay, and remember when you simplify that, this is like 15 over 1 times 1 over 4 to the 4th is 256. 3 squared would be 9. 4 squared would be 16. When you simplify all that out, you get 135 over 4,096, which is approximately 0.033, which is about 3.3%. Phyllis is not very good at bridge. Okay. Okay, last thing. On your graphing calculators, you can create the rows of Pascal's triangle on your graphing calculators. Go to the y equals on your graphing calculator. In y sub 1, I want you to put in 6 and then the combinations and then put in x, and then we're going to do a table start at 0 and the delta table count by 1s. Okay, so on your graphing calculator, this will create rows of Pascal's triangle. So if I wanted the 20th row, I don't want to have to go all through all the 19 rows before. So go to y equals, put in 6 and then the math key, left arrow to probability, go down and pick combinations, and then just use the xt theta n key to get x in there. Okay. Okay, then go to table set right above window on the top row. Do second function table set. Start the table at 0. Count the delta table, count by 1. Make sure it's auto. Okay. Okay. Okay, then do the table right above the graph key. Okay, and look at the second column under y sub 1. Here's 1, 6, 15, 20, 15, 6, 1. If you go back and look at that chart, isn't that this one? Okay, so if you want the 6th row, and I would leave that in there for a while. So if you wanted to pick another, you can go back. If I wanted the 9th row, change that 6 to a 9, and then look at the table. Okay, the 9th row, the 1, 9, 36, 84. and that's going across figure in this row. Okay, that is a quick way to develop the Pascal's triangle on the calculator. Okay, so you can use the y sub 1, you can use the tables. Okay, okay, that should get you started on that. Part of that is back on the mutually exclusive and inclusive, and then there's 3 problems on the binomial theorem.